Hello. So in this video, I'm going to go through the steps you need to get a erosion rate, a basin-wide erosion rate from cosmogenic nuclide concentrations, usually beryllium-10. And I'm going to use a template that I've got prepared within the lsdtopotools notebook page. So if you start from the lsdtopotools notebooks folder and you go into lsdtopotools and cosmogenic examples, there's an erosion template. So I'll just click on that. And once you go in here, there's going to be a link to Google Colab. So if you just click on that link, you will end up here in the erosion template. I've already done the first few steps of this. So you install lsdtopotools. You have to install something called Conda Colab, which allows you to get Conda packages, and then you install lsdtopotools from that. That whole sequence of things takes a little under 2 minutes. And you can just check to see if it works by running one of the command line programs. So one of them is lsdtt basic metrics, and you do a -v and you'll get the version. So I'm working in version 0.9 right now. I'm also going to download some topographic data from Open Topography, and we have a wrapper for that in lsdtopotools. To do it, you need to have your Open Topography API key as a text file. And so every time you start a new Google Colab session, it starts from a blank file canvas. So you're going to need to have that file and drag and drop it in to the file system. So I'm going to drag and drop that file in over here, and I can close that now. So in Colab, you have these little things on the left, one of which is the file explorer. So you need to drag and drop that API key into there. There's another video about how to get that API key. Okay, so I'm just going to run through this template explaining the steps, so it's all clear what you need to do. But if you've got your own data, you basically will do something slightly different from this template. You just change the location and some of the file names, and you should be able to run your own cosmogenic samples. So the first thing we need to do, we need to download a couple of data sets. These are some climate data sets that will give pressures for cosmogenic. They affect production of cosmogenics. So we download these two data files. And actually, I can show you that they've just turned up here. So nsep2 bin, those are binary files. And anyway, there's two files you need. Then you go into, if you have your location where you've got your samples, we can just download the location using our wrapper. The only thing you would really change here is you would just change the latitude and longitude. If you wanted to, you could kind of change the name of the areas. So I'm downloading from a place in Baja, California. To get these coordinates, you go onto Google Maps and you just right-click and it will copy the latitude and longitude. So you just have the lower left coordinate, upper right coordinate, and you should get the site you want. So I'm just going to grab that. And then, again, you don't need to really know what any of this is. Just copy and paste it. What this part does is it downloads data from Open Topography. So that might take a few seconds here. Again, for your own file, you would change the latitude and longitude and get your own topographic data. I'm using, in this case, COP30 is the Copernicus 30-meter global data set. There's several choices in Open Topography, but Copernicus 30 is probably the best one. So I pretty much always use Copernicus 30. The next part of the template is just a way to make sure your data is in the right place or you've downloaded the right place. So again, you're not really going to change this. All this is doing is making a hill shade and plotting it. So it just helps you show that you're in the right place. This is the mountain range I want. Now, for the cosmogenic analyses, you need a couple of parameter files. I've got this little template in here that writes the correct parameter files. So it's basically taken whatever you called the data set and writing the files with the right file name. You probably don't need to change any of these parameters. So the first one is a minimum slope for a filling algorithm. You don't need to change that. These two are something about snapping your cosmogenic locations to the channel network. Again, I wouldn't change those. The last thing on here is the muon scaling. There's a few options here. The Braucher-Borchers one is probably the most up-to-date. So again, I wouldn't change any of this. And so that is a parameter file. And then the next one is something called crnrasters.csv. And that's a pretty simple file. All it contains is the path to the main raster. So you don't really need, well, you wouldn't change any of those really, unless you wanted, say, a different muon scaling scheme. But again, I think the Braucher-Borchers one is probably the most up-to-date. Now you need to give the program your cosmogenic data. So how do you give it cosmogenic data? You need a CSV file, a comma-separated value file with these headers: sample name, the latitude and longitude, what nuclide you're using, the concentration, the AMS uncertainty, and the standardization. The standardization has to come from a list. There's some documentation about for the cosmogenic basin-wide erosion rate that tells you what the different standards are, but the most common is this 2007 KN standard. KN is for Kuni and Ishizumi. So you can make that file yourself offline. In this case, I'm just making up some numbers. So again, the top line of your CSV has to have exactly this series of headers, and then I've actually just made up some numbers here. So I picked some points. In reality, you'll have collected a sample, so you'll need to put in the latitude and longitude of the sample. You need to put in the nuclide. I haven't fully tested it on, it should work for carbon-14, but I didn't test it for this template. So if you're using this template, beryllium-10 is guaranteed to work. You can try it for aluminium-26 and carbon-14 and let me know how it goes. And then you have the concentration, atoms per gram, the uncertainty, and then the standardization. So that has to go into every line. So in this case, I've made up 3 samples. These are not real samples. Those are not real concentrations. There were no measurements. I'm just making these up. In your case, you would put in your actual data. Okay, and you can also, in this case, if you want to change your file name, you can. I didn't actually change the file name here, but this command shows you what the file looks like. Then you can also tell it the CSV file name. So if you already have your own file, you don't need to write the file. You can just upload the file, so drag and drop it into this file system, and then you need to tell it what the file name is. Okay. And then this next thing just copies that file into the right file name to run the analysis. So this little thing makes a copy of that file with the right file name, because the basin-wide erosion rate code is sensitive to the file names. You have to have the right file names. Okay, if you want to see where the points are, just to make sure they work, there's another bit of the template. again, you don't need to really know what this is doing. All you need to do, you just run this code and you can see where your points are. So these are the 3 points in my map. And then once you do that, you run this next bit of the code. You don't need to change anything, just control enter, and it will print out the basins where the cosmogenics are. So some ways that could go wrong is if you haven't downloaded a big enough DEM to capture the entire basin. You have to catch the whole basin. So you might run this code, look at the basins, and a few of your samples will be missing, and you'll just need to have a bigger clip of the data. Okay. Yeah, and I will say you need these 3 files. So you need the CRN rasters. We made that in an earlier step. You need the CRN param file. We made that in an earlier step. And you also need the CRN data, which we just made. Again, you could write that file yourself. Okay, the next step is, so you can skip this step, but I've included it here because we can see what it's doing. So you can make your topographic shielding raster, and actually this example is just setting the topographic shielding to have no topographic shielding. And it's based on this article by Roman DiBiase, who argued that the topographic shielding is sort of offset by the increased production from sloping surfaces. So to do this, I have these parameters here, which basically switches off the topographic shielding. It produces a raster that has all the same topographic shielding, which is none. It just, the way the topographic shielding works is that you get a raster of values of 1. But anyway, I can run this, and that will produce an updated topographic shielding raster. After you do this, it makes a new comma separated value file, which has this extra word in it, shield. So that allows you to run this kind of unshielded raster. So I'll just show you what that looks like. So this is the rasters file. This was the original rasters file. So the original rasters file just had the file name of the DEM. This one has the file name of the DEM, comma, a 0, comma, a 0, and then the file name of the newly created shielding raster. These 2 zeros in between are for snow shielding and self shielding. So I'm going to show you in a second where we could put the snow shielding in if you want that. We can look at what that raster looks like. So I'm just going to plot the shielded raster. And basically it's all 1. So it's effectively unshielded. The next part is snow shielding. So you can make a snow shielding raster. There's a couple of different ways of doing this. I've done it in a very simple way. So there's 2 options. There's a bilinear option, so that just has the snowpack increasing to a certain elevation, peaking, and then decreasing after that. And you can set the gradients of the ascending limb, the descending limb, and the peak elevation. And the units of the snow shielding are in atoms per gram per meter square. Or actually it's per centimeter square. So that is the bilinear one. There's also a different method called the Richards method. If you're using snow shielding, you probably have done the research on this. So the Richards method has a few different parameters, but I'm just using this bilinear one here. So I run that, and I can look at that CRN raster. So if you'll remember the last step, the CRN rasters had a 0 for the snow shielding. This snow shielding bit's a little bit underdeveloped, so it doesn't actually update the rasters file. So there's still a 0 here. We need to manually update that rasters file. So I have a little, I just have a little line here which will update manually that snow rasters here, and this is the new set of rasters that includes this snow shielding. And we can look at what the snow shielding raster looks like. Okay, so that looks fairly good. Now, the next bit is to get the erosion rates. There's 2 bits in this template. One is without the those extra shielding things, and one is with the extra shielding things. So I said I was running this this shielding where you don't have topographic shielding, and I did that as a separate step. You can actually do it in a oneer by just taking these 2 parameters and copying them into the main erosion rate, but I'm doing it separately just to show you what the results are. I might regret this because it takes a little while to run. So let's start running this. So this is where I'm using the full analysis. This will actually go through topographic shielding. It takes a little while, and then you will end up with some erosion rates. Well, actually, that one ran quite a bit faster than I thought it would. Here's the next one. So this is with the extra shielding parameters. And the way they are differentiated is just in the file name here. So that's file name, just UTM here, and then the one with the shielding has shield in it. So just wait. That ran fairly fast. And the final thing we can look at is just the output of the data. So this is the one without the shielding. This is the one with the shielding. So you can see the 2 erosion rates are slightly different. So if you want to run your own cosmogenic samples, you go through the same template and you just change the file names, change the location. You might set your own snow shielding parameters and you would put in your own concentrations, but you should be able to just swap out a few code blocks in here and you will get your topographic analysis.